Swayam Prabha. Digital India. Educated India.
And as with nodal analysis, I will write this in a matrix form as some matrix multiplying the vector of variables, which is the vector of mesh currents, equal to the source, the vector of independent sources, which is V1 minus V2 and 0. And here you will have R1 plus R3. So this is what is multiplying I1. And the next would be minus R3 and minus R1. So this is for mesh number 1. The second equation is for mesh number 2, and you will write minus R3, R2 plus R3 and minus R2. And finally for mesh number 3, minus R1, minus R2 and R1 plus R2 plus R4. Okay. So any questions on this? Because I had already done nodal analysis earlier, I went a little quickly through this, but if some part is confusing, please ask me. Now, all I did was, I first identified mesh currents, that is currents in each mesh in clockwise direction. Then I express every branch current as in terms of mesh currents, and they will come out to be either the mesh current itself for branches along the periphery of the circuit, and for branches which are common to two meshes, it will be the difference between two mesh currents. Then I wrote KVL in terms of these mesh currents, and finally I grouped the coefficients for each variable I1, I2, I3, and then wrote the whole equation as a matrix times the vector of unknowns equals the vector of independent sources, or a matrix of independent sources. Okay. Any questions so far? Okay. Now you can see that this structure is analogous to what we had with nodal analysis when we had only resistors and current sources. Okay. First of all, what are each diagonal elements? What are the diagonal elements? What are the elements on the diagonal of this matrix? Please try to answer this. So in the diagonal, in the first one, I see R1 plus R3. Second one, I see R2 plus R3. And the third one, R1 plus R2 plus R4. What are these? Okay, I think many of you were able to easily answer this one. It's the sum of resistances in each mesh. Okay. Now similarly, so the diagonal elements are sum of resistances in each mesh. Okay, and the off diagonal elements, you see that this element in the matrix notation, this would be called A12, and that is the resistance that is common to mesh 1 and mesh 2. Okay, so this is mesh number 1, mesh number 2 and mesh number 3, and this is common to mesh 1 and mesh 2. Okay. So the off diagonal elements are resistances that are common to meshes. Okay. Now you can see the analogy with nodal analysis very easily. So first of all, I will compare nodal analysis of a circuit having current sources and resistors versus mesh analysis which of a circuit with voltage sources and resistors. Now in case of nodal analysis, the variables are node voltages with respect to reference node, and in case of mesh analysis, the variables would be mesh currents in clockwise direction. Now all branch voltages will be either some node voltage or difference of two node voltages. A branch can be connected between some node and the reference node or between some two nodes. Okay, if it's connected between some node and reference node, then the branch voltage equals the node voltage. If it's connected between two nodes, then the branch voltage is the difference of two node voltages. And in case of mesh analysis, each branch current is either a mesh current okay. Now for branches on the periphery, on the boundary of the circuit, this will be the case, okay, because those branches will be part of only one mesh and the branch current equals the mesh current, or it will be the difference of two mesh currents, okay. So for branches in the middle, again, by taking the analogy of the map, that will be the borders between two states. The current in those branches will be the difference between current in the left branch and the current in the right branch, okay. So the current in one will be in one direction, the current in the other one will be in the opposite direction, and this happens because we choose all mesh currents in the clockwise direction, okay. And finally, if you write out the KCL equations and group the variables and so on and write it in this neat matrix form, you will get conductance matrix times the vector of node voltages. So this is the vector of unknowns, okay. So this V with a bar underside denotes a vector, and vector is nothing but a matrix, but it has only one column, okay. Equals the source vector. And in case of mesh analysis, you will have the resistance matrix, which consists of resistances only, times the vector of unknown currents, that is the mesh currents, equals the source vector, which consists of voltage sources in each mesh. When I say source vector, obviously I mean independent sources. Okay? And continuing the comparison, the conductance matrix G has, first of all, it is symmetrical, and it has diagonal elements which are sum of conductances and off diagonal elements which are, and when I say off diagonal, if it's the element ij in the matrix, conductance between node I and node j. Okay, and in fact it's the negative of that. Okay. Similarly, the resistance matrix is symmetrical and the diagonal elements will be sum of, when I say sum of conductances in the nodal analysis at that node, and here it will be sum of resistances in that mesh. Okay, and the off diagonal elements, the element ij would be the resistance common to node, sorry, mesh I and j. Okay, in fact it's the negative of that one. Okay, so by the way, all these are true when you have only resistors and current sources in nodal analysis and resistors and voltage sources in mesh analysis. Okay. So this is just to point out the duality between nodal and mesh analysis. You start off with KCL in nodal analysis, KVL in mesh analysis, and in a particular case, when you have a circuit with only current sources and resistors for nodal analysis and only voltage sources and resistors for mesh analysis, you get a neat structure for the equations which consists of a symmetric matrix times a vector of unknowns equals the vector of independent sources in the circuit. Okay, and also the matrix elements can be written down by inspection in case of nodal analysis by looking at conductances at each node or conductances between different nodes, and in case of mesh analysis, the total resistance in each mesh or conductances common to the resistances common to each the total resistance in each mesh or the resistances common to two meshes. Okay, any questions so far? Now there are some questions about including current source in mesh analysis. I will discuss that shortly. Okay, so now I think the simple case is pretty clear. We'll just take a numerical example just to get some practice. Or rather, we'll reserve the example for later. Let's have mesh analysis including a current source. Okay. This is the circuit I had earlier. And let's say instead of this resistor R3, I have a current source I1. Okay. Let's say this is the case. Now, as usual for mesh analysis, we have to write KVL. Now, what is the complication here? I would like to have answers from the participants. I want to go ahead with mesh analysis for this circuit, and I initially took a circuit with only resistors and voltage sources. Now I've added a current source. What is the problem? What is the complication with going ahead with mesh analysis for this circuit? So I hope the question is clear. Now, we have already done this. We have addressed a similar question while doing nodal analysis, which includes voltage sources. Okay. Nodal analysis, we write KCL equations, and KCL says sum of currents at every node equals 0. Now, when you have voltage sources, when you have resistors, the current is related to the voltage across the resistor. When you have voltage sources, the current is not related like that. Any current can flow through the voltage source. That's why we were not able to write the KCL properly, because we don't know the current through the voltage source. Now, similarly, my question is, if you have mesh analysis and you have current sources, what exactly is the complication? Again, a couple of people have raised their hands, but today the audio setup is such that I will not be able to hear your questions. So all your questions have to be through the chat window. Okay. Okay. So the problem is the following. So while writing KVL for this mesh, we have to say that the voltage across R1 plus the voltage across the current source equals the voltage across the voltage source. But a current source can have any voltage across it. Okay, for a resistor, the voltage across the resistor is the current through the resistor times the resistance value. So we can express the voltage source, voltage across the resistor in terms of the current through the resistor. Whereas a current source by definition can support any voltage across itself. So we cannot express the voltage across the current source as something related to the current value. Okay. So the problem is unknown voltage across the current source. Okay. So if you recall, when you had nodal analysis and voltages, you had the complication because of the unknown current through the voltage source. Okay. So this is the issue. Now how do we work around this? What did we do in case of nodal analysis? When we had nodal analysis with voltage sources, what was the thing that we did? How did we get around the problem? So my question is, when we had nodal analysis with voltage sources, what did we do? We don't know the current through it, so what did we do? So what we did was to define an auxiliary variable for the current through the voltage source. Now that gave us an extra variable and also an extra equation because of the voltage source, and we were able to write down the equations, and also for hand analysis we were able to combine two of those equations, effectively giving us a super node. Okay, so here the procedure we follow is exactly the same. What we don't know is the voltage across this current source. Let me call that Vx. Okay, so if I write the KVL equation for mesh number 1, okay, I will have the voltage drop across R1, which is R1 times I1 minus I3, okay, because this is common to mesh number 1 and mesh number 3. This is mesh number 3, and here I have mesh number 2, okay. This is the voltage drop across R1 plus Vx equals V1. This is for mesh number 1, and for mesh number 2 we will have R2 times I2 minus I3 minus Vx equals minus V2. Okay. Once Vx is defined with this polarity, when you go around the second mesh, you will have minus Vx. Okay. So if you look at the drops going clockwise, you will have the current in R2 times R2 minus V2 minus Vx equals 0, and V2 is moved to the right hand side. Sorry, plus V2 minus Vx equals 0, and V2 is moved to the right hand side. Okay. So now what we have is an extra variable. Now to solve for the extra variable, we need an extra equation. By the way, the equation for mesh number 3 remains exactly as it was before, because mesh number 3 is not modified in any way by adding this current source. Okay. So where do we get the extra equation from? My question is, by defining the voltage across the current source to be Vx, we have got an extra variable in our set of equations. To solve for the extra variable, we also need an extra equation. So where is the extra equation? So let me call this like I did before. This current I will call I1, and this current I will call I2. Okay, and let me just change this to I0, just so that I don't have two I1s in the circuit, and as RP answered, this I1 minus I2, which is this branch current, is known, that is defined by the current source, and that will be equal to I0. Okay. Now we did exactly this when we had nodal analysis. When a voltage source was connected between node 3 and node 4, let's say, we said V3 minus V4 equals the voltage source value. So that gives us the extra equation. Okay. So the extra equation is nothing but the definition of the current source. Okay. So if I put all of these things together, what I will get, and I will write it directly in the matrix form. I'll have mesh currents and the voltage across the current source as the variables. Okay. Then for the second mesh, we'll have and for the third mesh, we will have and the last one will be just a definition of sorry, here I would also add plus Vx, and in the second one minus Vx. Okay, so that's what we had. I wrote the last entries incorrectly. I have plus Vx here and minus Vx over there, and also finally I'll have I1 minus I2 equals I0. So that means 1 minus 1, that gives me I1 minus I2, and that is equal to I0. Okay. So in my variable vector I have this extra stuff, and my independent source vector consists of voltage sources and the current source. Okay. And this matrix, which I will continue to call the resistance matrix, has resistances as well as some dimensionless quantities. Okay. So the setup is still in terms of resistance times the variable vector equals the source vector. Variable current vector equals the source vector. But this variable vector also consists of this auxiliary variable, which is the voltage across the current source. And similarly, the right hand side vector consists of independent sources, which consists of voltage sources as well as current sources. Okay. Now, while doing hand analysis, this increased number of equations is not a good thing. You would like to reduce the number of equations. Okay. So then the answer is very clear. Again, we followed all these steps while doing nodal analysis with voltage sources. So I will go through it a little quickly. If I sum these two, okay, KVL around mesh number 1 and KVL around mesh number 2, what happens is this Vx cancels out. And this is not a coincidence. This will always happen because Vx is defined to be across some branch. So on in one of the meshes which contains that branch, it will appear as plus Vx, and in the other mesh it will appear as minus Vx. Okay, so it will always cancel out. And if I add these two equations, what I will get is